In this module, we're going to study fluids, and in this video, specifically fluid statics, which means we'll be studying fluids that are at rest, not moving. So first of all, a fluid is defined as either a liquid or a gas, and the first thing we need to know about is density. This is a Greek letter rho that's usually used for density, and density is mass per unit volume. So here's an example. We've got a reservoir that's got an average depth of 40 meters, and it's got a surface area of 50 square kilometers. We want to find the mass of the water. Okay, so we're going to use this equation, but we're going to solve it for mass, so the mass is equal to the density times the volume. And the volume is the area times the height. So that surface area was given in square kilometers, so the first thing we need to do is convert that to square meters. And there are 1 times 10 to the 6 square meters per kilometer. Remember, there's 1,000 meters per kilometer, but when you square it, it's 10 to the 6 square meters per square kilometer. Okay, so then that gives us 5 times 10 to the 7th, and then we multiply that by the average depth, which is 40 meters. So that gives us 2 times 10 to the 9th cubic meters, and that's the total volume of the water. So now the mass is going to be the density of water, which is 1 times 10 to the 3rd kilograms per cubic meter, times this volume, and we get 2 times 10 to the 12th kilograms. The next thing is pressure. Now pressure is defined as force per unit area. The units are newtons per square meter, and that's usually called a Pascal and abbreviated PA. So note that a force that is distributed over a very small area can generate a large pressure. So in other words, when this value is extremely small, even though this might be not that large, the pressure can be extremely big here. Okay, so pressure varies with the depth of a fluid. So water is a good example. As you descend deeper in the water, the weight of the water above you increases, so therefore the pressure increases. So a little bit more quantitative expression for that. Since we're talking about the weight of the water above you, the pressure would be mg divided by A, where mg would be the weight of the water. But mass is equal to the density times the volume. And as we saw in the previous slide, volume is equal to area times height. So therefore, pressure is equal to the density times area times height times g divided by A. But as you can see here, we've got A in both the numerator and the denominator, so therefore pressure is equal to the density of the fluid times the height or the depth times G. Okay, so a simple example of this, calculate the depth of water you have to descend to reach atmospheric pressure. So we're going to use this equation here, and we're going to solve it for H. That's going to be the depth you'd have to descend, so that's equal to P divided by the density times G. Now, atmospheric pressure is 1.01 times 10 to the 5th newtons per square meter, so you can look that up in your textbook. This, as we mentioned before, is the density of water. Also, there's a table in the textbook that has densities of all different materials, times 9.8. So you work through the units here, you get 10.3 meters. So if you descend in water 10.3 meters, you actually have 2 atmospheres of pressure on you. Atmospheric pressure, which is always there, plus the additional pressure exerted by this 10.3 meters of water. Pascal's principle says that a change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and the walls of the container. All right, so the best way to understand this is to give an example, and hydraulics is a great example. We've got a diagram over here that shows two pistons here and here. We've got a fluid in here, and we are exerting a force down here, F1, and that's exerting a pressure because there's an area here, A1, and then we have this force, A2, and this larger area, A2. Okay, so since this pressure and this pressure have to be equal, P1 and P2 have to be equal, then that means that F1 over A1 is equal to F2 over A2. F1 over A1 has to be equal to F2 over A2. Or, if we rearrange terms, then F2 over F1 is equal to A2 over A1. So that means that if A2, this area here, for example, is 20 times larger than A1, this area, then that means that F2, this force here, will be 20 times larger than F1. So that means that if F1, for example, was 20 newtons, then that would mean there would be an output force here of 400 newtons. So hydraulics is used in car hoists, for example, and various types of machinery where we need to multiply this input force. Gauge pressure and atmospheric pressure. Gauge pressure is the pressure over and above atmospheric pressure. So therefore, the sum of the gauge pressure and the atmospheric pressure is what's known as absolute pressure. Okay, so this diagram here, these three diagrams show something called a manometer. And on this situation here, it's an open tube on both ends, and so that both ends are open to the atmosphere. So both of the levels of the liquid here are the same. Now the liquid here is often mercury on manometers, but doesn't necessarily have to be. Okay, so this diagram over here shows, I don't know what that is, a balloon maybe, and that is exerting some extra pressure here, and as a result, it pushes this level of liquid upward a bit. So we can see down here that the absolute pressure is equal to atmospheric pressure plus the height of this column times the density of this material, if it's mercury, for example, times G. So this term right here is H times rho times G. That would be the gauge pressure. Now this diagram over here shows a jar of peanuts that are vacuum packed, and so the pressure inside there is actually less than atmospheric pressure. So you can see here that atmospheric pressure is pushing down here, and this pressure is less, and so therefore it's elevated on this side. And so in this case, the gauge pressure is actually negative, and so the atmospheric pressure would be, the absolute pressure would be the atmospheric pressure minus this product of H times rho times G. By the way, sometimes pressure is expressed just in atmospheres, which is the approximate atmospheric pressure, and that's equal to 760 millimeters of mercury. This pressure is sometimes just expressed in millimeters of mercury, which is also equal to 101.3 kilopascals. Now this is the same pressure as we used before, only we used 1.013 times 10 to the 5th pascals. So if you convert that to kilopascals, you end up with this 101.3. Buoyancy and Archimedes' principle. So you probably have had the experience that picking up a rock or anything heavier is easier in water than it is in land. And that's because of buoyancy. And this comes from the fact that the water pressure below the object is greater than the water pressure above the object. And that's the case because of the difference in height. There is a lesser height above the object than there is below the object. Okay, so if we look at this diagram over here, we can see right there, this object here is in the water. So this is F1, this is the force that the fluid is pushing down from above. And this is F2, this is the upward force. Now, F1 is equal to the pressure times the area. And the pressure would be P1, that would be the downward pressure here, and that's equal to this height times the density of the liquid times G times this area. So now we look down here for F2. This is the force that the liquid is applying upward here, and that's equal to this upward pressure, P2, times this area. And the upward pressure would be equal to H2, which is this bigger height here, or depth, times the density of the liquid times G times this same area. Okay, so the buoyancy is going to be the difference between these two forces. And so therefore, that is going to be equal to the density of the fluid times G times this area times the difference in these two heights. So the product of area times this delta H, the difference in the heights, is equal to the volume of this thing. So we can say that the buoyant force is equal to the density of the liquid times G times this volume. But the product of density times volume is mass. So therefore, the buoyant force is equal to the weight of the liquid that is displaced when this object is lowered down. And that is Archimedes' principle. The buoyant force on the object immersed in the liquid equals the weight of the fluid displaced by the object. Archimedes' principle is going to tell us whether an object is going to float or not. And if the object's density is less than water, it's going to float. If its density is greater than water, it's going to sink. So the reason why the object sinks is that its weight is greater than, I should have said the weight here, should have had the word weight in here, than the weight of the volume of the water that it displaces. So therefore, the weight of the object is greater than the buoyant force. So we've got the weight acting down, the buoyant force acting up. The weight is bigger than the buoyant force, and so it sinks. Now, if the object floats, then the fraction of the object submerged is given by this expression right here. So this is the volume of the object that is submerged divided by the total volume of the object. Now, the volume that is submerged has to be the same as the volume of the fluid, because it's going to displace that same volume of fluid, divided by the volume of the object. Now, density is equal to mass over volume, so volume is equal to mass divided by density. So this is the mass of the fluid divided by the density of the fluid. This is the mass of the object divided by the density of the object. So we divide this by this, and the mass of the object and the mass of the fluid have to be the same. So they're going to cancel out, and so we're left with this ratio of the density of the object divided by the density of the fluid. So the fraction, then, of the volume submerged is equal to this ratio of the density of the object divided by the density of the fluid. Now, when the fluid is water, then this ratio is called the specific gravity. And we can use specific gravity to determine the density of object. So here's a little example here, pretty simple problem. A woman floats in fresh water when 95% of her body is submerged when her lungs are filled with water, with air. She'd be drowning if they were filled with water. What is her average density? Okay, so all we need to do, we know the fraction of her body submerged, 95%, and we know the density of water. So her density, her average density with her lungs filled with air, is 0.95, that's 95%, times the density of water. Density of water is 1 times 10 to the third kilograms per cubic meter, so therefore that comes out to be 950 kilograms per cubic meter as her average density.